My talk is titled Automated Detection of DCIS in Whole Slide Images. So ductal carcinoma in situ, or DCIS, is a non-obligatory precursor of invasive breast cancer. Most DCIS patients undergo breast-conserving surgery to have their tumors removed. However, some receive additional radiotherapy to reduce their risk of recurrence. So the overall project goal is to identify those patients with extremely low risk of recurrence that do not need additional radiotherapy. So as I said, the DCIS is removed from the patient, sectioned and stained with H&E, and imaged in an Aperio slide scanner at 20 times to produce the whole slide images. So data is stored hierarchically at different resolutions, and you need special viewing software to view them. So we want to be able, as Andrew mentioned, we want to be able to extract imaging features from these DCIS regions and ignore the irrelevant areas around them. So we have Pathologist Annotations on DCIS images, and these annotations were converted from the Aperio format to our new Sedin format. So it's hard to get pathologists to segment large numbers of these images because it takes a lot of time and it's really expensive. So we want to be able to automatically recreate these segmentations on new data, which is the primary focus of my project, as automatically localizing DCIS in whole slide images. As you can see, this is a non-trivial problem. So in the diagram, image A shows a normal duct, whereas B through D show DCIS ducts, and you can see the DCIS all looks quite different, and the normal duct looks qualitatively somewhat similar to the DCIS one. So there's high interclass variability and low interclass variability, meaning we have a very complicated segmentation problem for which we'll be using CNNs and deep learning to solve. So the data set we'll be using, as I said, we have scanned tissue sections from DCIS patients that underwent breast-conserving surgery. We have 202 whole slide images with full ground truth DCIS annotations. They're split up amongst training, tuning, and testing sets as shown on the slide, and 10% of the training set was used as a validation set to monitor for early stopping. So the network I chose to start with is known as a UNet. It's very common, very powerful network for segmentation. Most of you have probably seen it, but I'll quickly just go through. So the image inputs on the downsampling arm, and it performs a series of 2 convolutions and then a pooling operation, and it does that sequence over and over and over again until you reach an encoded representation of the image. And then the network starts doing convolution, up convolution sequence of operations, and at the end of each of those you concatenate the feature maps of the equivalent size from the downsampling arm with your new set of feature maps in order to preserve spatial information. So you perform that sequence of operations over and over again until you reach the original size, and you get an output segmentation map, which is just a probability of each pixel in the image representing, or whether each pixel in the image is DCIS. And so in order to analyze these whole slide images, you have to extract patches because you can't fit an entire whole slide image into CPU memory. So the question I'm trying to answer is, what is the optimal field of view to resolution ratio at which you should extract these patches? So given my constant patch size of 256 by 256, there's a trade-off between having high resolution with small field of view patches versus low resolution, very wide field of view patches. And you can see in the diagram there various patch sets, 20 times, 10 times, and 5 times. And the blue square there represents the equivalent field of view patch in 1 resolution step up. And so the next question I wanted to ask is, would I be able to, we trained a UNet on each of these patch sets in order to answer this question. And the next question I wanted to ask is, can you overcome this trade-off with a multi-resolution UNet in which each of those patches from the previous slide would be treated as a single input sample and be input together into the network? So I designed this modified UNet architecture where the downsampling arm is split into 3 convolutional tracks, 1 for each input size, and so we perform the same convolution pooling series for each input or downsampling arm until you reach the encoded representation, at which point they're all concatenated together. And then you perform the same upsampling arm with a convolution, deconvolution sequence. And again, you can concatenate the equivalent size feature maps to your upsampling arm. And again, you result in an output probability map. So this network in the diagram, I've given the designation 3RM, you can see there. And then the second multi-resolution network that we used was just to concatenate all 3 input images into a single 9-channel image and use the ViewNet as I described previously, which I've given the designation 9CH there. So all of our networks use a simple post-processing scheme. So the network runs on all the patches in a whole slide image, and they're stitched together, and the post-processing operates on that stitched together probability image. And the pipeline just consists of a thresholding operation, a morphological opening, and a morphological closing. Morphological opening is supposed to get rid of small white grains in an image, and closing is supposed to fill in small negative gaps in the image. So the threshold and morphological radius were treated as hyperparameters, and were optimized using the tuning set. And to evaluate these networks, we had a few metrics. So the dice coefficient measures positive overlap between 2 binary images. The equation is shown there. TP being true positive pixels, FP being false positive pixels, and FN being false negative pixels. We also use a modified F1 score. Mathematically, the F1 score is identical to the dice coefficient. However, we calculated it at the object level, or duct level. And so when our ground truths often group large numbers of ducts into one region, whereas the networks often identify those ducts individually. So we've modified the F1 score so as to not penalize finding multiple objects within a single ground truth region, because we still want those regions to be counted correctly. The downside to this is that the F1 score is no longer symmetric. So flipping the ground truth and test images would give you a different result. And we also use the AUC, or area under the ROC curve. So looking at some results, you can see the 5 times network achieved the greatest dice score, whereas the multi-resolution 3-arm network achieved the highest F1 score, showing it has greater duct detecting capabilities. This finding is supported if you look at the ROC curves. You can see the 5x curve and the 3-arm curve are the top 2 there, with the highest AUCs. So this 5x being the best is interesting, as it implies that wider field of view patches are actually advantageous compared to the high resolution ones. And that kind of makes sense because when pathologists look at images, at least for DCIS, they often make most of their decisions by looking at just the low power at first, and they fine-tune or refine their decisions by looking at the high-powered. And then, so it kind of makes sense. The other advantage that 5 times has is that it runs in much less time than any of the other networks. So this is just an example of the 5x UNet probability map output displayed over top of the whole slide image, just the probability map, so there's no post-processing. And you can see there's the blue outlines show the ground truth pathologist segmentations. And you can see there's like sharp drops at the edges of, or sharp drops in probability around the ground truth edges. So this network is actually doing quite well. You can see all the ducts are fairly well defined. There's a few kind of weird areas here where the duct is kind of empty and the network doesn't really pick up this white area. And so another useful comparison to make is comparing to human level performance. So we asked a second pathologist to independently annotate all of our slides on the test set. And the labels here, the blue outlines show definite DCIS, whereas the yellow outlines show probable DCIS. And you can see between these two images, there's quite a discrepancy between which ducts are labeled as probable versus definite, and also the style in which ducts are grouped together. So there's a bit of discrepancy there. And finally, just showing the same results table, but with the second annotator metrics shown there. And we did a Wilcoxon sign rank statistical test between each of the models and the second annotator. So the p-values are shown in the next column, and the stars just show which p-values were less than 0.05. So the key takeaway here is that the 5x network performs pretty well, not significantly different from the second annotator for dice score and for F1 score. Same with the multi-resolution network, but the F1 score for the multi-resolution network was significantly greater than the second annotator. So yeah, in conclusion, we show that low resolution, wide field of view patches can offer superior accuracy and time benefits when training a UNet for segmenting DCIS. Patches from various resolutions can be combined to overcome the resolution versus field of view trade-off, but at the expense of runtime. 5X and multi-resolution networks show comparable performance to a second annotator. The drawback of the study is that the test size is relatively small for our duly annotated data, and it's only from a single institution. And future work will involve extracting imaging features from regions surrounding the DCIS and making predictions about patients' risk of recurrence. So I'd just like to acknowledge my supervisory committee, our on-staff pathologists, and the rest of the Martel lab. Thank you.
Very nice. Thank you very much. Any questions? Any questions? Yes.
Hi, thank you for the talk. You're going from 5x to 20x. But you know that a lot of analysis is done at 40x and perhaps more.
Yes.
Yeah. Yeah. So did you look at that, and secondly, because pathologists are going to combine their analysis at different levels, so, and you were combining them, but the results, I would like to know what results you got when you combined this. The different axes, the results for different axes.
Okay.
5x, 10x, 20x.
Yeah. So yeah, I did combine them, and it showed slight improvements. Unfortunately, the images we had did not have 40x available, so I couldn't include that in the analysis. I would expect that it wouldn't do as well at just 40x because the field of view would have to be very, very, very narrow. So there's no contextual information involved. But that's just my guess.
Any other questions? Yes, in the back. Was there
Do you have an idea why both 5x and 20x perform better than 10x, which is in the middle? Looking at F1 score and I score.
Yeah, I thought that was kind of odd as well. It's almost as if you want to double down on one, just have very high resolution or very high field of view, and trying to go for a balance in between just gives you the worst of both worlds, if that makes sense.
Yeah, I think there was another question over there.
Hello, good presentation. I was just asking about the cases which your tool didn't pick up as DCIS or incorrectly labeled something which was not DCIS as DCIS. How many of them were ADH or LCIS? Did you have a pathologist look into that?
No, we unfortunately didn't have a pathologist review the results slides, so I don't know. Actually.
I think that would be something interesting to do. So whereabout the results lie in the spectrum,
yeah,
because you can get atypical ductal hyperplasia, and then did you divide your DCIS cases into low grade and high grade to see which of the DCISs was being more accurately picked up by your tool?
No, unfortunately, we didn't have access to that grade information.
Okay.
Yeah.
Thank you.
But yeah, that's a good point, though.